Sebastian, my man, what were the questions you had? By the way, I finally got my, I hate mornings where I run around for a minute.
So I know what the independent and dependent variables are, but how do I explain them?
Okay, so if you look at that one with like force and acceleration, okay? So your independent one is the one that you can control. So if you look at that demo I did yesterday with the fan cart, so here was the track, and here was that cart, okay? We had that fan on top of it. So we were looking at two things. We were looking at force, and we were looking at acceleration, okay? So what I could control was what speed did I set the fan to, okay? Did I set it to low? Did I set it to high? So I controlled how much force was being applied to the system. So the acceleration of the cart was dependent upon how much force that I applied to it, okay? So that's how you know, it's like, which one do you manipulate? So if you look at, I will use this later when you do projectile motion, so you can do the same thing. Here's like, oh, okay. So this is a marble launcher. It even says marble launcher on it. So I can control, like, I can pull this down to the first notch, okay? We'll talk about potential energy later, right? And then I can flip that, and then it's going to launch that marble up, okay? So then I can pull it down to the second notch, okay? Right? So, like, if you look at this in terms of what I control, like, how far down I pulled the spring. The height that the marble goes to is dependent upon that. So in this case, my independent variable would be how far I pull down the spring. And the height that it goes to is dependent upon that. So my independent variable would be the number of notches that I pull down. My dependent variable would be the height of the marble. Okay? Got that idea? Mm-hmm. Okay. All right. So I want to make sure everybody's kind of cool on that back side when you get to like question number 18. So if you look at that one where you have F equals mv squared over r. Okay, and this is what we talked about yesterday, where this is, and we'll spend a whole lot of time talking about this. So this is how much force it takes to make something move in a circular path. So you have three variables: the mass that's on the end of the string, the radius, and how fast it goes, right? So if I'm traveling kind of slow, that's a little bit of force. If I make it go faster, right, that takes even more force. So, and if you all have experienced this equation, you're going, no, we haven't. Yes, you have. You experience this equation every time you make a turn in your car, okay? Because objects don't want to travel in circles; they want to travel in straight lines. So if you want to make your car travel in a circle, that's going to require a force. Oh, this is the mass of the car. This is how fast your car is going. And this is the radius of the curve. So if you take a really, really tight turn and you have a really small radius, oh, that's a big force. If you take a big gradual turn like this, oh, you're dividing by a bigger number, the force becomes less. Okay? So here's all I want you to see. Oh, radius gets bigger, force gets smaller. Mass gets bigger, force gets bigger. Velocity gets bigger, force really gets bigger. So because anytime something is squared, that makes it a quadratic function. So if I double this velocity, my force goes up by a factor of 4. If I triple my velocity, the force goes up by a factor of 9. Okay? So any small changes to the velocity will make a huge impact on that amount of force that you need to make that turn. So on that one on that last question where it says, like for example, if the radius is halved, what will happen to the force? Okay, and again, there's two ways that you can do this. Option number one, you do smash mouth physics. You go, I'm going to have a 1 kilogram mass moving at 1 meter per second with a radius of 1 meter. Okay, boom, there you go. Plug in numbers and say, here's my initial set of conditions. Cool. Then you can say, all right, then I'm going to change it. I'm going to keep the same kilogram. I'm going to keep the same velocity, but then I'm going to have the radius. Oh, so then I'm going to divide by 0.5 meters. So if you like smash mouth physics, recalculate this, take 1 times 1, divide that by a half, calculate a new value of force. Okay? So if you like numbers, go with that process. If you like variables, go, okay, well that's mv squared over r. So my new set of conditions is going to be mv squared, and then that's r over 2. Oh, I'm dividing by r over 2. The 2 flips up, everything gets doubled. So I don't care what process that you have to do this, whether you like to put in numbers, whether you like to work with variables, I don't care. Just pick the process that makes the most sense to you, that you feel most comfortable with. Okay? So on the test, your first test is going to be on Friday. Okay? So I promise you, you're going to have questions like this. So make sure that you feel comfortable with whatever that process is. Okay. Any other questions at all on that assignment? Going once? Going twice? So get that handed in, staple that graph to the back, please. So Austin, stop that. So here's the last skill set that you need to do physics, okay? And this is this concept of significant figures. So if you think about it, every answer that you write in this class, and you're going to write a lot of answers, okay? You have 2 decisions that you have to make every time you write an answer in this class. You have to decide, number 1, how many digits are you going to write down? So let's say that you punch numbers into your calculator, and your calculator says the answer is 0.057326417. Okay? So you've done this calculation, and the calculator says this is your answer. Okay? So what you have to decide is how many digits are you going to write down? Are you going to write down all of them? Are you going to write it as 0.5? Are you going to write it as 0.57? What are you going to do? So that's the first decision that you have to make. How many digits are you going to write down when you get an answer? The second decision that you have to make is what units are you going to put on it? Are you going to put velocity? Oh, it's meters per second. Are you going to put force? Are you going to put newtons? Are you going to put a distance? Oh, that's meters. Okay? So those are the 2 decisions that you have to make every time you write down an answer in this class. What units and how many digits that you're going to write. So when you talk about calculations in physics, all the calculations that we do, if you look at the entire history of physics, have been based upon some type of measurement, right? So whether it's the mass of the Earth, sometimes we have to measure really, really big quantities. Oh, hey, what's the mass of the Earth? That's a really, really big number, 5.979 times 10 to the 24th kilograms, okay? What's the distance to the moon? Oh, 3.844 times 10 to the 8th meters, okay? What's the mass of a proton? Oh, 9.11 times 10 to the negative 27th kilograms. What's the mass of an electron? Okay, really, really small numbers. So in physics, you deal with these extremes. Extremely small measurements of subatomic particles, extremely large measurements, the mass of the Earth, okay, the diameter of the Milky Way galaxy, whatever that is. What's the mass of a black hole, okay? Or you have more common things that we're going to measure. Oh, what's the mass of a tennis ball? What's the mass of this block of wood? What are the dimensions of this block of wood? So every time you measure something, you're limited by what we call the precision of the measuring device. So when you talk about measurements, there's 2 key terms that you have to have, and you have to keep these straight. One is accuracy, okay, And these definitions are on the back of the lecture notes that I've given you. Okay, so these are there. If you flip them over, these are on the back side of it. And then you have precision. And these are kind of related, but they're not, certainly not the same thing. So let's talk about accuracy first. So if you've ever done like target shooting, okay, where you have like a bullseye, and you're trying to hit a particular target, okay? If you're an accurate shot, what does that mean? David, if you're an accurate shot, what does that mean?
You hit the target.
Yeah, there's a bullseye. There's a designated point that you are trying to hit, okay? And if you're an accurate shot, you hit that target. You hit the bullseye. So the same thing is true of measurements. If something is accurate, what that means is that there's a designated target, okay? There is a measurement that you should get. So if you can only talk about the accuracy of a measurement if you know what the scientifically accepted answer should be. So like one of the things you're going to do is that you're going to find a measurement of the acceleration due to gravity in this room, okay? We're going to measure this eventually. And what we should get is 9.80 meters per second squared. That's the accepted value for the acceleration due to gravity on the surface of the Earth. So when Paige gets that measurement, she can compare her answer to 9.8 meters per second squared. If she does this measurement and she gets 9.75 meters per second squared, that's pretty good, okay? Because she is pretty close to the accepted value, okay? Now, ray gun does it, and he gets 14 meters per second squared. It's like, oh man, that didn't go so well, man, okay? Maybe he mismeasured something. Maybe the time was wrong. Something was wrong, okay? But here's the point. This is what I kind of call the Siri test. If you can ask your phone, what is the accepted value for the acceleration due to gravity on the surface of the Earth? And Siri can find you an answer. Oh, here's what I have found, okay? You can talk about the accuracy of your measurement. Mass of the Earth, distance to the moon, whatever, okay? So let's say, here's another example. Then you can kind of compare that value. So let's say that I give Ray Gun the task of measuring the width of my table, okay, from here to here. And he measures it, and he's off by a meter. It's like, really? Okay, this is what it should be, and you're off by a meter. It's like, come on, man, you're better than that. I said, okay, Ray Gun, I'm going to give you another chance, okay? I want you to measure the distance from Mays High School to the moon. Come back with me tomorrow morning. Okay, so Ray Gun's like up all night, man. He's pounding milk and Oreo cookies, and he comes in the next morning and his hair is all disheveled, and he hasn't slept, and he's using meter sticks and stopwatches and all this stuff, right? He comes in, slams down a piece of paper, and he goes, Mr. Burkamp, this is what I've calculated the distance from Mays High School to the moon to be. I look at it, and he's off by a meter. It's like, wow, that's pretty good. So if he measures this distance and he's off by a meter, it's like, oh man, you can't measure for jack, right? You measure the distance from Mays High School to the moon and you're off by a meter, it's like, man, you are a measuring savant. So just because you're off by a meter doesn't mean that that's a bad measurement. It just depends on what you're trying to measure. So some of the things that we're going to measure in this class, we can talk about the accuracy of them because there is an internationally accepted value. Other times we're not going to be able to talk about the accuracy. So one of the labs you're going to do is you're going to push a cart against a wall and it's going to bounce back. And you're going to calculate the velocity of the cart. Okay? Well, you can't talk about the accuracy of that measurement because there is no internationally accepted value for the velocity of the cart that you're going to push and bounce off the wall in my room. Okay? There's no accepted value for it. So sometimes you'll be able to talk about accuracy, and sometimes we won't. Okay? Like if you talk about the speed of sound. Oh, there is an accepted value for the speed of sound, 343 meters per second. If we measure the speed of sound, we can compare that to that value because there was an accepted value for that number. So accuracy, you can only talk about accuracy if there is an accepted value. And sometimes there isn't an accepted value because that's the whole point of doing a lab. It's like, oh, we're going to set up our own data set. Maybe we can't talk about accuracy. Now, precision. Let me give you a simple example about precision. So, let me hand this out. So, Austin, stop that for a second. Okay, so here's what I've given you. I've given you an index card. And I've given you a measuring device. And this is just a measuring device that I made up. I want to call it a widget. Okay? So a widget is anything that you want it to be. In this case, a widget is going to be the measuring device that I gave you. So when you look at the widgets that I gave you, some of you were quite disappointed because you just have 0 and a 1. Okay? And you're like, oh, seriously? It's like, I got screwed on this deal. Okay? Others of you have widgets that have 0 and 1, but then you have marks like this, okay? All right? Others of you have widgets that are marked off 0 and 1, and then you've got a whole bunch of marks on there. 1, okay? So here's what I want you to do. The best way to figure out this whole concept. So what I want you to do is I want you to take the widget that you have, and I want you to measure the width of the index card across like this, using the measuring device that you have. And then when you get that done, I want you to come up here, and I want you to write that under the measuring device that you have. So, like that, or the one that has all of those little divisions on it. Okay? So, take your widget, take your index card, measure across like this, and then come up here, and I want you to write that down underneath whichever measuring device that you have. Okay, so just take this pen and write that underneath whichever one that you think you have. Baton handoff. Come on, Milkman. That might be your new nickname.
Please.
What?
That'd be funny.
Oh, really?
I'm telling you. I have groups. I should.
Okay?
There's not
Yeah.
walking back here. It's on.
Okay.
You go. Look at that.
That was on purpose.
Okay.
That actually slams it.
And don't be influenced by what others have written. Don't be afraid to go out on your own.
Dude, what? You literally just looked at what I had.
No, I didn't know.
Yes, you did.
You
You clearly did.
No, Seb, I really folded it. Look, I folded it.
Getting 0.64 is stupid, bro. Look at this. Like, this isn't even reach anywhere close.
Oh, I got that one.
Yeah.
Nice.
Yeah, that's what I'm saying.
I just guess so. That would be cool. And I'm going to put on my
It is
so I put
nice.
on.
It's pretty cool.
You put your phone?
Yeah, I started that to use that.
Yeah.
I like it because I can always face the class.
Nice, you have 2 decimals. That's not a decimal.
Oh, yeah, don't trip over my cord. Don't trip over my cord. That's going to be bad. Okay.
0.63.
Huh. Are we still going? Okay. So, let's chit chat about this. The good news is that some of these are right, but the vast majority are not. And you're going, "Ah, seriously? Okay, so let's chit chat. So, what's the fundamental difference between the three measuring devices? Let's start with just that idea. What's the difference? Sebastian, milkman.
How much, like to the hundreds or to the tenths that each one gives?
Okay, the number of divisions, right?
Yeah.
So this one is just 0 and 1, and you were so disappointed that you got that. Okay? And then you got the tenths, right? Okay? And then you got this one that has all these little divisions on it. So let's just start with this concept. So for those of you that had the 0 and the 1, okay? So you had this, right? You're measuring this distance across here. So who put down like that 0.6? Okay. So are you absolutely confident, would you bet huge sums of money that that 0 is correct? Okay, because you could look at this and go, oh, it's somewhere between 0 and 1. How did you get the 6?
Just kind of guesstimating.
You guesstimated, right? Okay? So these two measurements are correct based upon this measuring device. So here's the rule. You can only estimate one more place value than what you know for certain. Okay? So on this one, these two measurements are correct. Okay? Because you can only guess one more place than what you know. Okay? I think you had measurement envy. I think that's why, because you
Yeah.
put down like the 0.6.
Yeah, I felt the need to put it down. I don't know.
Okay, all right. So, but when we're measuring, we have to operate within certain rules and parameters. Okay? So when you're measuring, you can only estimate one more place than what you know for certain. Okay. So let's talk about these 2.63 measurements. Okay, so who put up one of these? Okay, Milkman. How'd you get the 0.63?
Well, I looked at my measuring thing, and it was like about a third of the way between 0.6 and 0.7.
Okay, so now we're going to follow this trend. So I'm going to draw yours a little bit bigger, okay? And here was 0.6, and here was 0.7, and I'm guessing the edge of that card was about there. Ballpark?
Yeah.
Okay. So, do you know the 0 is correct?
Yeah.
Would you bet huge sums of money on the 0?
Yeah.
Okay? What about the 6? Would you bet huge sums of money that it's somewhere between 0.6 and 0.7?
Yep.
Knowing values, right? There is absolutely no uncertainty whatsoever in that, right?
Mm-hmm.
How did you get that 3?
I looked at it, and it looked about a third. So
Okay, so this is a guess, right? So if you look at this trend, okay, you guess one more place value than what you know, right? So these two are correct, okay? Now Tanner, you put the 0.635, right? Why is yours not correct? What did you go too far on? The numbers, right? Because here's the deal. Tanner would actually be correct if we had this one. Because here's the deal. The door has to swing both ways. So if I look at all of these measurements that are here, if this is all I saw, was this set of measurements, which measuring device do I think you had?
the middle one.
I'm going to think you had the middle one. Because it looks like you know the 0, you know the tenths, and you estimated the hundreds. So for all of you that got this one, what should have you done? Yes, you should have went one more place, okay? Because otherwise, it looks like you have this measuring device. So you didn't put enough decimal places out there. Now, so who has one of these? Revise your measurement. Look at yours again. What would you put down? I want you to go one more place beyond what you know.
You're so goofy. 0.641.
0.641. Okay? So here's what I'm guessing that you saw. I'm going to draw this really big. There's 0.6. There's 0.7. And I'm guessing that edge was something like that. Okay? Just past this mark. Okay? So here's the deal. Now, if you put 0.641, ooh, now here's what you're telling me, is that you know this is right. You know the 0, you know the 6, you know the 4. Which place value did you estimate? The 1. So you know the whole number, the tenths, the hundredths, you're estimating the thousands. Now, here's what's going to give you more trouble than anything, and that's zeros. Okay, it's like, ooh, because here's the problem. Let's say that it had been exactly at 0.64. It had been exactly at 0.64. Okay, so here's the deal. If you just write, even though it's exactly at 0.64, if you put 0.64, you're not conveying enough information. So a 0 is just as valid a guess as any other number is. Okay? That 0 is important because it's conveying information about the measurement. Okay? Now, if it had been exactly 0.6, let's say you have the one that has all those divisions on it, and it's exactly at 0.6. If you just put 0.6, you're thinking that you have that measuring device that just has 0 and 1 on it. Let's go, well, that's not right. So, if it's an exact measurement, you're going to have to put zeros on the end. So here's the process. If you don't know whether to put a 0 on it, assume this. Let's say yours had been exactly on that mark. Think to yourself, what if it had been over a little bit more? If it was over a little bit more, I'd write that as 0.645. So if you don't know what to do, if it's exactly on a mark, think through the process and go, oh, right, okay. If it had been over a little bit, I could estimate that thousandth place. If you can estimate that thousandth place, that means that 0 is valid. So this 0 on the end is important because it's conveying information about the precision of the measuring device. So zeros on the end are important because it's going to tell you the precision of that measuring device. Okay? So now that you kind of got this idea, because depending upon which measuring device that you have, you're going to come up with different values for the exact same length. So now, of all of these measurements, which one is the most accurate? Or can you talk about the accuracy?
Was there an accepted value?
If you went to your phones and said, hey, Siri, what's the accepted width of an index card measured in widgets? Do you think Siri is going to give you an answer? No. I cannot talk about the accuracy of these measurements because there is no internationally accepted value. Okay? I can talk about the precision of them. Which measurement is the most precise?
The last one.
The last one, because that has the most divisions. So you can always talk about precision, okay? You can always talk about precision, but you can only talk about accuracy if you know the accepted value, okay? And that's the difference. So like, if you remember back to your Chem 1 days, okay, you had like the digital scales, and the Chem 1 scales, if you remember, like you were massing magnesium or whatever, and it might read like 2.56. Okay, so the Chem 1 scales go out to the tenths and they go out to the hundredths place. Okay, the scales that I use in AP chemistry, they read like 2.5678. Those scales go out to 4 decimal places. Now, these scales actually cost $5,000 a piece. That's what you pay for to get that increased precision. So the Chem 1 scales, they're not bad. They have a certain amount of precision. But when I teach AP chemistry, because we have to have more precise measurements, those scales go out to 4 decimal places. So the more decimal places that you go out to, the more precise that measurement is. Makes sense. Okay. Now that you kind of get this idea, now the rules of significant digits are going to make more sense. So when you're talking about these calculations, here's the basic idea. Every problem that you're going to do in this class is going to be based upon some values that I give you. How high does Paige jump? Okay? How far does Austin throw a ball? Okay? What's the mass of Jackson? And we're going to figure out the gravitational attraction between Jackson and the center of the Earth. Okay? So every problem that you're going to have is going to be based upon some data. So here's your overriding theme, and if you keep this in mind, the rules of significant digits make more sense. Here's the overriding theme, is that when you do a calculation, okay, and you write down an answer, you can't make your answer look more precise than the data that you have to start with. So in other words, if you have sketchy data, you can only have sketchy answers. If you have really, really good data, you can have really, really good answers. Okay? So if you go to, let's say your measuring device has that one that's only marked off to 0 and 1. Okay? You don't have really good data. So when you do calculations, you can't sit here and go, oh, my answer is 0.7521 widgets. So let's say you multiply, add, subtract, whatever. You do some mathematical calculation. And this is the answer that you put down. And if I look at this, I'm going to think, wow, you had a really, really cool measuring device because you knew tenths, hundredths, thousandths, and you guessed the 10,000th place. Wow, that's cool, right? Because if this is what I see, that's what I'm going to think. You had some phenomenal measuring device. And then I'm going to ask you, like, what was your measuring device? It was marked off to 0 to 1. Really? So you had this measuring device that's marked off to 0 to 1, and you're going to get an answer that goes tenths, hundredths, thousandths, 10,000ths? No! If you have sketchy data, you can only have sketchy answers. Now, if you had that one that's tenths, hundredths, thousandths, and you were estimating that, okay, hey, this is somewhat believable. You can have good calculations because you have good data. So if you keep just that thought in mind, sketchy data, sketchy answers. Really good data, really good answers. Okay? And if you just keep that thought in mind, the rules of significant digits make a lot of sense. So, when you deal with significant digits, there's 2 distinct sets of operations that you're going to do. The first ones we'll talk about is addition and subtraction. Okay? So when you add or subtract, you are limited by the least precise measurement. Okay? So let's say that we're going to add some widgets together, okay? So we're going to take 12.6 widgets and we're going to add that to 100.47 widgets, and we're going to add that to 5.2 widgets, okay? So we're going to take 12.6, 100.47, and 5.2. So which of these measurements is the most precise? The first one, the second one, or the third one?
Second.
Second one. Why?
It's big.
Not necessarily that it's big.
Is that, you know, the tenths.
That's right. It isn't based upon the size of the number. It's based upon the decimal places that you have. Okay? So this number out here isn't part of the discussion in terms of precision. This is what's going to determine the precision, is the number of place values. So these two measurements here, you can only estimate the tenths place. This one, I know the tenths, I'm estimating the hundreds. So when you're adding or subtracting, here's the easiest thing to do. Go out here, if you want to, if you're not sure, and put an arrow over either the most precise or the least precise measurement. I don't care. Let's go with the least precise because that'll probably be a little bit easier. So since these numbers are only known to the tenths place, when I write my answer, I can only write that as the tenths. Now here's the problem that I face as the teacher from this side of the room. You all are excellent at plugging numbers into calculators. Okay, you guys are great at it. But it's almost like you view the answer that shows up on the calculator screen as like an oracle, like a message from the calculator gods. No, it's true. I've seen this long enough. And it's like you all feel like you have a moral obligation to write down all the digits that the calculator gives as an answer, okay? Because it's like you're afraid that you're going to upset the calculator gods, and your calculator is going to start giving you wrong answers if you don't write down all of the digits. Like, oh, the oracle has spoken, I must write down all of the digits. Or the next time I plug in 2 plus 2, the calculator is going to tell me the answer is 5. Okay? Let me assuage your fears. Your calculator does not care what digits that you write down. It honestly does not care. It has a lot of other things to worry about. What you write down is not part of the story. Okay? Your calculator does not care. Okay? You'd like to think it does, but it doesn't. I've talked to them. They don't care. Okay. So that's one thing that I struggle with, because you fear that you're going to upset the calculator gods. The other thing I struggle with is the T word. And that's the case that you're going to have to think when you write down your answer. Because it's so much easier just to blissfully write down all of the numbers that show up on your calculator screen. Like, oh, I'm just going to write them all down. I don't have to think, okay? You can't do that. You're going to, at some point, going to have to think and go, wow, how many digits do I put down? So here's what I want you to do. Somebody take, speaking of the calculator gods, somebody take 12.6, add that to 100.47, and add that to 5.2, and tell me exactly what the calculator gods say the answer is.
118.27.
100 what?
18.27.
118.27. So according to the calculator gods, this is your answer, 118.27. Now, if you write that down, okay, if you write that down, I'm going to think that all of your measurements were out to the hundredths place. Okay? Were all of your measurements out to the hundredths place?
Nope.
No. What was the least precise measurement? The tenths place, right? So therefore, I have to round this to the tenths place, because that's my least precise measurement. So, since what you want to do is look to the number to the right. If this is 5 or above, what are you going to do with that number?
Round it up.
Round it up. So I'm going to write this as 118.3. Okay? Now, here's why this is important. If I see this, I'm going to think, oh, okay, right? The least precise measurement was out there to the tenths. That's what I've got. Boom. Here we go. Because if you write 118.27, I'm going to think that your measurements, all of them were out to the hundredths place. And they weren't. The tenths was the least precise place value. Okay? Got that idea. Now, this is even worse. I'm going, seriously, again. So let's say that you're going to take 25.35 and you're going to add that to 41.650. Okay? So those are my two measurements. 25.35, and I'm going to add that to 41.65. Okay? So what's my least precise measurement? Tenths, hundredths, thousandths.
Tenths.
What's my least precise measurements? Tenths, hundredths, thousandths. Hundreds, right? This is my least precise measurements in the hundreds, right? Now, Sebastian, punch this into your calculator. Tell me what the oracle says.
67.
67. So your calculator says the answer is 67. Now, if you put down 67, why is that bad? Because if all I see is 67, what am I going to think about your measuring device?
Least precise is the ones.
Yeah. If you just put 67 and think, man, you had a horrible measuring device. You can only measure like the whole widget. You know, it's like, that's about 67. It's a ballpark, right? So if you put 67, then you're not conveying enough precision. So what are you going to have to do here? Jackson, what do you think I'm going to have to do?
Add 2 zeros together.
Yeah. Now, I can put this as 67.00. That's my good answer, because this is going to convey the precision of that measuring device. So sometimes you're going to have to add zeros on the end. So that's why I'm telling you, zeros will give you more fits than anything else. But if you just remember, right, when you're adding or subtracting, it's the least precise place value. So in this case, my least precise place value is to the hundreds. That's why I have to write that answer as 67.00. Okay? Yes?
When you get to a bunch of like larger numbers, like let's say you had like 5 numbers that went out to the thousands, but one that went out to the tenths. Would you like us to round the numbers before or after you get it done?
No. What you always want to round when you get to the end.
Okay.
Save those numbers and then round when you get to the end.
Good.
Okay? All right. Got that idea. So, Austin, stop that. Stand up. Okay. So here's the last big concept. And this is counting the number of significant figures. So we're just going to work through some examples. So let's say that we want to know the distance from here to May South High School. Okay? And I tell you it's about 9,000 meters. okay? That's like 9 kilometers, that's about 5 miles, okay? So in this situation, I'm going, how far is it from here to May South? It's about 9,000 meters. It's a ballpark estimate, okay? That's all it is. And sometimes in science, that's all we can measure, or that's all we need. So, like sometimes, like if we're measuring really big distances, hey, like what's the distance from the Earth to the Moon? Okay, we know it's like 384 million meters. Okay, it's a ballpark. What's the mass of the Sun? It's about 59,000 kilometers, or kilograms, okay? So sometimes we just need ballpark estimates, because that's all we can measure, right? So on this one, when I say it's about 9,000 meters, that is literally, it's just an estimate. It's about 9,000 meters, okay? I didn't take a meter stick and like lay it out and count the exact number of meter sticks, right? It's about 9,000. And sometimes that's good enough. So, but if I contrast that and I say, what's the distance to May South? And I say it's 9,500 meters, okay? Now, which of these two measurements do you think is more precise? The 9,000 or the 9,500?
9,500.
9,500, right? Because this is just, hey, it's about 9,000. This one's a little bit more precise because, again, it's the same process. I know the 9, I'm estimating the 5. Now, if I say, what's the distance to Mays High School? And you go 9,505.2 meters. Now what's happened to the precision?
It's come up.
It's gone way up. We set up like lasers, okay? This is a really, really precise measurement. That's a ballpark. How far is it over there? About 9,000. How far is it? About 9,500, right? A little bit more precise. This 9,500.2. This is a really precise measurement. So, again, here's the idea. How you write answers conveys information about the measurement. So, one of the skills that you got to be able to have is the ability to count significant digits. So here's going to be your overriding theme. If there's no decimal place, no decimal point, you count left. If there is a decimal place, decimal point, then you count right. Okay? Now, so here's the deal. So you go to this 9,000. You find there's not a decimal place. How far is it? It's about 9,000. There's no decimal place. You find the first non-zero digit and you count everything to the left. So if there's no decimal place, these zeros are here. Okay, we're not going to count them. You find your first non-zero digit, which is the 9, and you start counting there. Oh, that's difficult. That's just 1. So this would have 1 sig dig. So the zeros in this case, stay with me here, are like freshmen. They're just taking up space, but they're not important. Okay, which is true of a lot of freshmen. Okay, what do freshmen do? They take up space. Are they important? No. Let's be honest. You all were freshmen. Don't act like you weren't. I made fun of you all when you were freshmen. Now, so this is have 1 significant digit. We're going to go to this one. Same process. There's not a decimal place. You find the first non-zero digit, which is this 5, and then you count everything to the left. So this would have 2 sig digs, because this is showing a higher degree of precision than this one is. So these are freshmen, but they're just freshmen. Now, if you have a situation like this, where you had 905,000 meters, same process. This is still a freshman, but it's like, this is a freshman that's cool enough to hang out with the upperclassmen. So it's just like, it's still a freshman, but we'll let him in. So maybe this is like your little brother or little sister or something like that, right? So here's the same process. There's not a decimal place. You find the first non-zero digit, and you count everything to the left. So this would have 3 significant figures, okay? So this has 1, this has 2, this has 3. So it's kind of like Tinder. If there's not a decimal place, if you've ever seen the Tinder app, which I haven't, but here, I guess here's the story. If you don't like someone, you sweep left. So if there's not a decimal place, you sweep left, and you start counting, okay? So this has 3 sig digs. All right? Got that. Now, let's go down to this one. If there's a decimal place, which is, there is, now we sweep right. So if there's a decimal place, you find your first non-zero digit, and you count everything to the right. So you would start here with this 9. You're going to go 1, 2, 3, 4, 5. So this would have 5 significant digits. So if there's a decimal place, go left, count right. If there isn't a decimal place, you go left and you keep counting left. So this would have 1, 2, 3, 4, 5 significant digits. Now, where you run into troubles is decimal places. So let's say that you have a really small measurement, like 0.053. Okay? Got a decimal place, you're going to count to the right. So here's a decimal place. You find the first non-zero digit, which in this case is this 5, and you count everything to the right. These zeros are freshmen. They're just taking up space. We don't count them. Okay? So this is going to have 2 significant digits. Now, if you have 0.05300, these zeros are significant because of the fact that they're showing the precision of the measuring device. They're saying, this is why these zeros count, because they're showing how precise that measuring device is. So it's the same process. Here's a non-zero digit. You count everything to the right. So you go 1, 2, 3, 4. That has 4 sig digs. Okay? Cool with that. Now, let's review scientific notation. I know at some point in your esteemed science careers, you all have been taught scientific notation. So, scientific notation, remember, you move the decimal place so that you have 1 place value to the left. So, if I were to put these numbers in scientific notation, the beauty of scientific notation is that all the numbers that you show are just the ones that are significant. Okay? So like in this case, I'm going to take this decimal place and I'm going to move that 2 places to the right. So this would be 5.3 times 10 to the minus second. Because remember, small decimal places have negative exponents. Okay? So this is going to be 5.3 times 10 to the minus second. If I were to put this number in scientific notation, I'd write that as 5.3, but then I'd have to put these zeros on the end to show that those are significant. So the beauty of scientific notation is that you don't have to guess. Anything that you put in scientific notation automatically is significant. Okay? It's automatic. There's nothing to think about. As soon any number in scientific notation conveys that measurement. So here's how this plays out. So when you multiply or divide, your answer is determined by the smallest number of significant digits. Okay? So let me just, this makes sense once you start to look at some examples. Okay? So let's say that we're going to measure the speed of a car. And let's say that it's traveling at 45.6 meters per second, which would be about 90 miles an hour, okay? Car's going pretty good, okay? And that car is going to move for 1.2 seconds. So imagine this. Here's this car, it's traveling at 45.6 meters per second. And it's going to travel for 1.2 seconds. I want to figure out what I get when I multiply this together. Now, here's the deal. The other thing that complicates the multiplication and division process is that you're going to end up with different units. So you also have to then incorporate dimensional analysis. So this is why we learn dimensional analysis before we learn significant figures. So let's start with what units I'm going to get. If I take meters per second and multiply that by seconds, Paige, what am I going to get out of that?
Meters, seconds over seconds. No, but the seconds cancel out.
Beautiful. So the seconds are going to cancel out. I'm left with meters. So I know my answer is going to be some number of meters. Now, because I'm multiplying, how many significant digits are in this number? 3. How many are in this one? 2. So my answer can only have 2 significant digits. So, Sebastian, punch this into your calculator. Take 45.6 times 1.2 and tell me exactly what the oracle says the answer is.
54.72.
54.72. Okay? So according to the oracle, this is your answer, 54.72. Can I put that as my answer?
No.
No. Because if I put this as my answer, you're going to tell me that every measurement that you had 4 significant digits. At best, this one has 3, this one has 2. So none of my measurements have 4 significant digits. So I can't put this down, but you go into Mr. Burkham, the oracle has spoken. My calculator says this is the answer. It's like, I don't care what your calculator says. It's not going to work. Okay? So how can I write this answer with 2 significant digits? Anika, what can I put down?
54.
Nope, close.
55.
55. So here's the deal. This answer can only have 2 significant digits. So I can only have these 2. But what I'm going to do is I'm going to look to this 7. This 7 is 5 or above, so I've got to round that to 55 meters. So there's my answer, 55 meters. Now, I'm going to change this up a little bit. Sebastian, I want you to take 45.6 meters per second, but now I want you to multiply that by 12 seconds.
547.2.
Now you get 547.2 meters. Ooh, now I can only have 2 significant digits. Ooh, this is a problem. So how can I write 547.2 with 2 significant digits? David?
550.
I can put 550. That's cool. Okay? Now, here's the deal. Is 550 the same as 550 with a decimal place on the end of it? Do these 2 numbers, 550 without a decimal place, have the same number of significant digits as 550 with a decimal place? If there's a decimal place, which direction do you count?
Right.
Sweet, right. Find the first non-zero digit. This would have 1, 2, 3. This has 3 significant digits. If you don't have a decimal place, which direction do you count? So I find my first non-zero digit. I count left. This has 2. So this has 2 significant digits. This has 3 significant digits. So I can't put that decimal place on the end. So one option is you put the answer like this. The other one is you go, oh, Mr. Burkamp, I like scientific notation. Good for you, okay? I'm happy for you. So how can I write this in scientific notation with 2 significant digits?
5.4,
Nope.
5.5,
Yep. Times 10 to the... How many places did you move that decimal place? How about 2? 1, 2, 2, 3. What's the difference? That's okay. Times 10 to the second. So you can either write it as 550, you can write it as 5.5 times 10 to the second. Now, let's say that had been 12.0 seconds and you actually needed 3 significant digits. So there's 3 ways you can handle that. If you actually needed 3 significant digits, one option is that you write it as 550 and you put a decimal place on the end of it. That's going to show 3 significant digits because you're going to count, there's that decimal place, you're going to count everything to the right, that's going to have 3 significant digits. Okay? That's an option. You could write it in scientific notation like this, because scientific notation shows everything that is significant. That's an option. Okay, that's cool. Or sometimes in the old style, you'd see it where you put a line over the top of it. So if you see it a 0 with a line over the top of it, and some textbooks will still use this style, this shows that it's significant. So here's the best analogy. This is like a freshman, but he's like your little brother, and you put your hand over the top of him and go, yes, he's a freshman, but he's cool. This is like the chosen one. So if you put that 0 over the top of it, or that line over the top of that 0, you're saying, yes, it's a nerdy little freshman, but he's with me, so he's cool. Okay? So if you ever see the lines over the top of zeros, that's what that information is conveying. Okay? Got that? So let's say we'll do one more. We're going to take 5,000, it's about 50.020 meters per second, and we're going to divide that by okay. So we're going to take 50.020 meters per second, and I want to divide that by 1.2010 seconds. Okay? So let's talk about this. Leave the numbers out of this. Let's talk about units. I'm going to take meters per second and divide that by seconds. Do I get meters? Because the seconds cancel out. Or do I get meters per second squared?
meters per second squared.
Meters per second squared. Beautiful. And that's the most common mistake that's made, is right here. And if you're not sure, take meters per second, multiply that by the reciprocal of 1 over seconds, you get meters per second squared. Now, those are my units. This is going to be an acceleration. So I'm going to have units of meters per second squared. How many significant digits are here? Which direction do you count?
Right.
Because there's a decimal place. So start here. 1, 2, 3, 4, 5. 5 significant digits.
Mm-hmm.
This one has how many?
4.
1, 2, 3, 4.
5.
Everything has 5 significant digits, right? So my answer has to have
5.
5 significant digits. So, Sebastian, tell me what the oracle says the answer is. So, the calculator, what does the oracle say the answer is?
41.648626114.
41.648.
62614.
Okay, and then da-da-da-da. Now, is this what I can put as my answer?
Nope.
No. How do I have to write that answer?
With 5 seed digs.
5 seed digs. So this is going to be 1, 2, 3, 4, 5. Okay? So since this is a 6, what's that number going to become?
A 9.
9. So that answer is going to be 41.649 meters per second squared. Now, here's the potential downfall. Let's say it wasn't, but let's say. Let's say that was 41.6496. Then what would you do? And you need to round it to this place value, but that's a 6. What are you going to do?
You change the 49 into a 50, but keep the 0.
Fantastic. Absolutely spot on answer. So you got to round this up, so you got to write that as 41.650 meters per second squared. Got it? Good? Grand? Stop that for a second. Let me hand out the assignment. Okay, so let me kind of get you through this. So, on 1 through 9, all I want you to do is count the number of significant digits. There's no calculations to do, and if you're not sure, up here at the top of this assignment, I've given you the rules and some examples, okay? So if you're like, I don't know what to do, go up here and look at these examples, okay? So 1 through 9 is just going to be however many significant digits that you have. When you get to 10 and 11, you're either adding or you're subtracting. When you add or subtract, do you worry about place value or the number of significant digits?
Place value.
Place value, not the number of significant digits. So when you get to number 10, what I would do, when you get to 10A, I would find the least precise measurement, which in this case is going to be like that 10.02. That's your least precise measurement. Put a mark, and go, that's my least precise place value, which means I'm going to round this answer to the hundredths place. So plug those numbers into your calculator, and you're going to round that to the hundredths place. On the back side, and by the way, when you get to this question down here on number 11 below number 7, it says, how is the last distant and the measured value different from the other values? Use the word while. So what you want to say is like something while the other one is So when you're trying to answer a question like on the bottom of that page, use the word while. You're going to say, this is this while this is something else. Okay? When you get to questions 13, 14, and 15, these answers I want in scientific notation. Specifically, I want them in scientific notation with the correct units. Now, if you're not cool with your calculator, when like you're doing that 6.66 times 10 to the negative 8, what you want to do is punch in 6.60, and then most calculators have an EE key. Do not type in times 10 because it's going to screw up your order of operations. So go 6.60, you should have like an EE key, and then punch in negative 8. Okay? Don't type in times 10 because it's going to completely jack up your order of operations. 15 through 18, you're going to do those. If you want to put the answers in scientific notation, you can. If you don't want to, hey, that's up to you. 19 through 24, you are back to counting number of significant digits. 25 through 30, you are going to figure out the mathematical operations. For now, don't worry about 31, 32, or 33. We're going to work 31, 32, and 33 in class tomorrow. Okay? So do not worry about 31, 32, or 33. That's the first thing we're going to do in class tomorrow. And then you can answer number 34. Okay, I'm done. You're on your own. What a long day.